Far out beyond Neptune, in the cold and shadowy reaches of our solar system, there exists a world so strange and enigmatic that even its name sounds like something from myth Orcus. This distant dwarf planet, drifting silently in the Kuiper Belt, holds secrets that challenge everything we think we know about the outer solar system. It's a place where the usual rules seem to bend, where unexplained phenomena linger just beyond the edge of our understanding, waiting for curious minds to unravel them. Today, we're embarking on a journey to explore not just one or two, but 25 of the most compelling mysteries surrounding Orcus, each one a puzzle piece in a grand cosmic story that's still being written. What makes Orcus so fascinating isn't just its distance or its size, it's the sheer number of unanswered questions that swirl around it. Why does it have such an unusually bright surface, almost as if it's reflecting sunlight in ways other similar worlds don't? How does it maintain such a perfectly synchronized orbit with Neptune, like a dancer moving in time with a partner it can't even see? And perhaps most intriguing of all, what could explain the tantalizing hints of geological activity on a world so far from the sun's warmth, where everything should be frozen solid? These aren't just dry scientific questions, they're gateways to wonder, invitations to imagine the possibilities lurking in the dark. As we delve into these 25 mysteries, you're not just watching a list, you're joining an exploration. You'll come away with a deeper appreciation for how much we still have to learn about our cosmic neighborhood, and why places like Orcus remind us that the universe is always full of surprises. From its mysterious moon, Vanth, to the bizarre chemical signatures that hint at processes we can't yet explain, each mystery pulls us further into a story of discovery that's as thrilling as it is humbling. So settle in, open your mind to the unknown, and let's venture together into the depths of space to uncover the secrets of one of the solar system's most captivating worlds. Our first great mystery takes us straight to the heart of Orcus's celestial choreography. This distant world is locked in a perfect gravitational dance with the giant ice planet Neptune. For every 2 complete trips Neptune makes around the Sun, Orcus makes exactly 3. This precise timing is what astronomers call a 3-to-2 orbital resonance. It means these two vastly different worlds, separated by billions of miles, are moving in sync like a carefully tuned metronome, their orbits harmonized by the invisible hand of gravity. What makes this so unusual is how clean and stable this relationship has remained over billions of years. You might expect such a delicate balance to be easily disturbed, knocked out of alignment by the gravitational pull of other planets or by close encounters with other objects in the chaotic early solar system. Yet Orcus has maintained this rhythm with remarkable fidelity. It suggests that its path was set very deliberately during the solar system's formative era, perhaps shepherded into this stable orbit by Neptune's own migrating path outward. This isn't a random occurrence, it's a fossilized record of a dynamic past, a clue that the outer solar system settled into its current configuration in a very specific way. This synchronization defies what we might consider typical. Many objects in the Kuiper Belt have been scattered into erratic, tilted orbits by gravitational encounters. Orcus, however, stands out as a pristine example of order amidst that chaos. Its resonance is so perfect that it almost feels engineered, as if some unseen mechanism guided it into this stable relationship. This forces us to reconsider the violence of the early solar system. It wasn't just a random billiard game of colliding planetesimals. There was also a profound underlying order, a music of the spheres where gravitational harmonies locked worlds into patterns that have endured for eons. Orcus's dance with Neptune is a primary piece of evidence for that ancient, elegant structure. Moving from its orbital ballet, we encounter a visual paradox that has left astronomers scratching their heads. Orcus possesses one of the brightest surfaces in the entire Kuiper Belt, reflecting a tremendous amount of sunlight for an object so far from the Sun. This high reflectivity, or albedo, is our second great mystery. It suggests a surface dominated by highly reflective water ice, which is strange enough for a world where temperatures hover near -240 degrees Celsius. But the plot thickens considerably when we look closer. Spectroscopy, the technique of breaking down an object's light into a chemical fingerprint, reveals that this brilliant ice is not pure. It's intermingled with significant amounts of a dark, unidentified material, creating a surface that is both gleaming and shadowy at the same time. This strange combination is a major puzzle. Cosmic radiation and constant bombardment by micrometeorites over billions of years should have darkened any exposed ice, painting the surface a dull charcoal gray. This process, known as space weathering, is exactly what we see on many other distant objects. Yet Orcus has somehow resisted it. Its ice remains conspicuously bright and fresh-looking, as if it were recently resurfaced. So how does it maintain this youthful complexion? One compelling theory points to cryovolcanism, the idea that internal heat, perhaps from the decay of radioactive elements or gravitational squeezing, could occasionally melt subsurface ices. This slushy mix of water, ammonia, or methanol might then erupt onto the surface, coating the landscape in a bright, new layer of frost and effectively erasing the evidence of space weathering. It's a process that suggests Orcus is not a completely dead world, but one with a hidden, sluggish geological heartbeat. The nature of the dark material mixed with this ice is another enigma. It doesn't match the spectral signatures of common organic compounds we see elsewhere, like the reddish tholins found on Pluto or other Kuiper Belt objects. This unidentified substance could be complex carbon-based molecules forged by radiation, or perhaps even primitive rock and dust that has never been altered by heat. Its presence creates a bizarre patchwork landscape in our minds, a world of brilliant, reflective planes slashed with dark, scarring veins of unknown matter. This surface isn't just a simple layer of frozen gas. It's a dynamic and evolving interface, a chemical record that holds secrets about the composition of the very building blocks that came together to form the outer planets. Unlocking the identity of this dark component would give us a direct glimpse into the primordial ingredients of our solar system. This peculiar partnership introduces our third great mystery, the origin of Vanth itself. The sheer scale of this moon relative to its parent world is a colossal puzzle. Vanth is estimated to be nearly a third the diameter of Orcus. To put that into a more familiar perspective, that would be like our own moon being not a quarter of Earth's size, but roughly the size of the entire continent of Asia. In the vast majority of planet-moon systems we observe, the moons are mere specks in comparison to their hosts, captured asteroids or tiny shards from ancient impacts. Vanth's substantial presence completely upends that expectation, suggesting its birth was anything but ordinary. Scientists are locked in a debate over how such an unusual pair could have come to be, and each potential explanation comes with its own set of complications. The most common theory for moon formation, especially in the dwarf planet family, is a giant impact. We believe Earth's moon was born this way, and the Pluto-Charon system is a famous Kuiper Belt example. Perhaps a colossal object sideswiped a young Orcus, blasting a huge cloud of debris into orbit that later coalesced into Vanth. This could account for the moon's size, but it also presents a problem. Such a violent, off-center impact would likely have left Orcus with a dramatically different rotation, spinning rapidly or perhaps even tipped onto its side. Instead, Orcus rotates at a measured, leisurely pace, showing no obvious sign of such a catastrophic event in its past. This leads to the other main hypothesis, capture. Could Vanth have once been an independent object wandering the Kuiper Belt, only to be gently grabbed by Orcus's gravity and pulled into a permanent orbit? While this sounds elegant, the mechanics are incredibly difficult to achieve. For a capture to happen without the smaller object simply speeding away or crashing directly into the larger one, a complex gravitational ballet involving a third body or a precise slow-down maneuver is often required. It's a cosmic game of chance that seems almost too perfect to have occurred for a moon this large, making the capture theory feel, for many, like an even greater long shot than a giant impact. The intrigue only deepens when we consider what we don't see. Detailed observations reveal no evidence of any other moons or a debris ring around Orcus. If a giant impact did occur, we would typically expect to find a family of smaller satellites or at least a dusty disk of leftover material, yet the system appears to be a clean, binary pair. This cleanliness forces us to consider even more exotic possibilities. Perhaps the Orcus-Vanth system is not a product of its local environment at all, but a primordial binary that formed together from the same swirling cloud of dust and ice at the dawn of the solar system, two partners condensing side by side from the very beginning. This would make them true siblings in a cosmic sense, forever bound together in their distant, frozen orbit. Each theory, from collision to capture to co-formation, paints a different picture of the solar system's violent and dynamic youth, and Vanth remains the silent, key witness to that ancient history. But this bright, icy surface holds an even deeper secret, leading us directly into our fourth great mystery, the strange and uneven patchiness of its reflectivity. While Orcus as a whole is brilliantly bright, that shine is not spread evenly across its entire face. Instead, it's a world of stark contrasts, a mosaic of dazzlingly reflective planes sitting side by side with regions of profound, light-absorbing darkness. This isn't just a uniform ball of ice, it's a planetary puzzle with pieces that don't quite fit, suggesting a complex and active history that we are only beginning to decipher. These albedo anomalies, as astronomers call them, are far more than just a simple color variation. They represent fundamental differences in the surface composition and, by extension, its history. The bright regions are almost certainly vast exposures of relatively clean water ice, acting like gigantic mirrors reflecting the faint sunlight back into space. The dark regions, however, are something else entirely. They absorb light rather than reflect it, and their spectral signature remains stubbornly unidentified. This patchwork quilt of light and dark is a clear signal that the surface is not some ancient, static landscape frozen in time since the solar system's birth. Something is actively altering it, repainting parts of this distant world in a process we don't yet fully understand. One of the most compelling explanations for this surface renewal is the possibility of cryovolcanism. Imagine not the fiery, molten rock eruptions we see on Earth, but a far colder and stranger phenomenon. Deep within Orcus, residual heat from the decay of radioactive elements, or perhaps heat generated by the gravitational flexing of its interior, might be enough to melt subsurface reservoirs of ice into a thick, slushy slurry. This mixture of water, ammonia, and other antifreeze compounds could then be forced upward through cracks and fissures, erupting onto the surface in a slow-moving, frigid lava flow. As this slush spreads across the landscape and instantly freezes in the vacuum of space, it would create a brand new, brilliantly bright layer of frost, effectively erasing any older, darker terrain and creating the stark albedo contrasts we observe from Earth. Yet cryovolcanism isn't the only potential artist at work here. Another process could be the seasonal sublimation of ices, a kind of slow-motion atmospheric dance. When Orcus reaches the closest point in its elongated orbit to the Sun, even the minuscule increase in solar energy might be enough to cause the most volatile ices on its surface, like nitrogen or methane, to transform directly from a solid into a gas. This process would leave behind a lag deposit, a concentrated layer of darker, less volatile material like rock or complex organics. As these ices sublimate in some areas and redeposit as fresh frost in others, it could create a constantly shifting pattern of bright and dark patches, a dynamic cycle of renewal and decay happening on a world we once thought was utterly frozen and inert. The mystery is amplified by the fact that we don't know the power source for any of this potential activity. Orcus is a small world far from the Sun and should have lost its internal heat billions of years ago. The mere suggestion that it could still be geologically active today forces us to reconsider our models of how these distant, icy bodies function. It hints at interiors that are more complex and potentially warmer than we ever imagined, perhaps insulated by layers of exotic ice or kept churning by the gravitational influence of its large moon, Vanth. Each bright patch on Orcus is a question mark, and each dark region is a shadowy secret, together forming a map that charts not just the geography of a dwarf planet, but the limits of our current understanding of the solar system. This brings us to a thermal conundrum that defies simple logic, our fifth great mystery: the perplexing temperature variations on Orcus. For a world so incredibly far from the Sun, you would expect its surface to be a monument to consistency, a uniformly and unimaginably cold ball of ice locked at a steady, deep freeze temperature. The Sun is little more than an exceptionally bright star from that distance, providing negligible warmth. Yet the data tells a different story. Observations, particularly in the thermal infrared spectrum, reveal that the surface of Orcus is not one uniform temperature. Instead, it exhibits surprising fluctuations, with certain areas registering as significantly warmer than their surroundings, a finding that directly contradicts our basic models of these distant, frozen worlds. These thermal anomalies are a major clue that something dynamic is happening on or within Orcus. A simple, inert ball of rock and ice would quickly radiate whatever minuscule heat it receives from the Sun back into space, achieving a bland thermal equilibrium across its entire surface. The presence of hotspots, however slight they may be, shatters that expectation. It points to an internal engine, a source of heat that is working against the relentless cold of space to create these warm patches. This forces us to confront a startling possibility. Orcus might not be the completely dead, frozen relic we assumed it to be. It could possess a warm heart beating slowly beneath a frozen crust. The potential sources for this internal heat are as fascinating as they are varied. The most straightforward explanation is the lingering warmth from the decay of radioactive elements locked within its rocky core, like potassium-40 or thorium-232. While this radiogenic heating is a common feature in larger planets, its effectiveness in a relatively small body like Orcus over billions of years is a subject of intense debate. Could its interior be sufficiently insulated by a thick mantle of ice to retain this feeble heat for so long? Another compelling theory involves gravitational tidal heating, fueled by its intricate dance with its massive moon, Vanth. As the two bodies orbit one another, their gravitational pull constantly flexes and squeezes their interiors, much like repeatedly bending a piece of metal until it becomes hot. This process is known to power the fierce volcanic activity on Jupiter's moon Io, and while it would be far more subdued at this distance, it could provide just enough energy to explain the strange thermal readings. The mystery is further compounded by the possibility that these temperature differences aren't solely driven from within. The unique properties of its surface could be playing a crucial role. We already know Orcus has a patchwork of bright, reflective ice and dark, absorbing material. These two substances interact with solar radiation in completely opposite ways. The brilliant white ice acts like a shield, reflecting most sunlight away and thus remaining bitterly cold. The dark patches, however, behave like an asphalt road on a summer day, absorbing a much higher percentage of the feeble solar energy that reaches them and converting it into heat. This creates a natural variation where dark terrains become subtle thermal islands in a sea of frozen plains. The true enigma lies in untangling this effect from potential internal heat. Are the warm spots simply these dark, sun-soaking regions, or are they windows to a warmer interior, where heat from below is welling up to slightly warm the surface? The answer likely lies in a combination of both, a complex interplay between external absorption and internal generation that makes Orcus a far more thermally active world than its location would ever suggest. These surprising temperature readings lead us to a visible and equally baffling feature of this distant world, its strangely smooth complexion. The sixth great mystery of Orcus is the conspicuous lack of cratering on significant portions of its surface. In a region of space as chaotic and littered with debris as the Kuiper Belt, every object is essentially a cosmic punching bag, constantly bombarded by wayward rocks and ice over billions of years. This relentless pummeling should leave a surface densely pockmarked with impact craters of all sizes, a permanent record of violent collisions. While some areas of Orcus do show signs of this expected scarring, other vast regions appear remarkably smooth and youthful, as if a giant celestial eraser had recently wiped them clean. This smoothness is a profound clue that cannot be overstated. It tells us that the surface we see today is not the ancient, primordial skin of Orcus from the dawn of the solar system. Instead, it is a relatively new layer, one that has been laid down after the most intense period of bombardment had already passed. Something has actively resurfaced this world, erasing the craters and creating these strangely pristine plains. For geological activity of this scale to occur, a significant source of energy is required, a force that can drive change on a global level. Finding evidence for such a force on a small, cold, and remote dwarf planet forces a complete rethink of what these distant icy bodies are capable of. The most compelling suspect for this planetary renovation is once again cryovolcanism. Imagine not a fiery explosion of molten rock, but a slow, oozing eruption of a thick, cold slush. This mixture, likely composed of water ice mixed with ammonia or methanol acting as a powerful antifreeze, could be forced up from a liquid or slushy ocean deep within Orcus's interior. As this frigid magma breaches the surface, it would flow across the landscape, filling in and burying any existing craters beneath a fresh, bright, and perfectly smooth layer of new ice. Each of these events would effectively hit the reset button on that part of the surface, giving it a geologically young appearance despite the object's ancient age. The patchy nature of this smooth terrain suggests these are not global events, but rather localized eruptions, painting the surface in a complex history of renewal. But cryovolcanism isn't the only process that could be at work. Another possibility is the gradual relaxation of the crust itself over immense timescales, a phenomenon known as viscous relaxation. Water ice, while solid and rock-hard at these temperatures, is not as rigid as stone. Over millions of years, the ice that forms Orcus's crust can actually behave like a very slow-moving fluid. Under the relentless pull of its own gravity, the steep ridges and rims of craters can slowly slump and sag, their sharp features gradually flowing to fill the empty bowls until the crater virtually disappears and the surface becomes smooth again. This process would be more effective on smaller bodies with weaker gravity, and the presence of any internal heat would dramatically accelerate it by making the ice even less viscous and more prone to flow. The combination of these processes creates a fascinating detective story written on the surface of Orcus. The smooth plains are not just blank spaces, they are active chapters in the world's history. Their existence directly implies that Orcus has retained enough internal heat to power these geological processes for a significant portion of its life, far longer than our standard models would predict for an object of its size. It suggests a world that is dynamically balancing heat loss against internal sources, whether from radioactivity, tidal forces, or the latent heat of formation. Every smooth plane is a direct challenge to the old idea of the Kuiper Belt as a deep freeze where everything is preserved unchanged for eons. Orcus is showing us that even in the most remote and frigid reaches of our solar system, the engines of geological change are still quietly, slowly turning. This peculiar tilt, known as its orbital inclination, is our seventh great mystery. Unlike most large objects in the Kuiper Belt that orbit the Sun in a relatively flat plane, much like the planets do, Orcus travels on a path that is significantly cocked, tilted at an angle of roughly 20 degrees. This isn't a minor deviation, it's a pronounced lean that sets it apart from the crowd, suggesting its history was far more tumultuous than that of its neighbors. An orbit like this doesn't just happen. It's a scar, a permanent record of a powerful gravitational encounter that knocked it off a more conventional path, sending it into this lofty and isolated trajectory. The real puzzle lies in identifying what exactly could have delivered such a forceful shove. In the early, chaotic days of the solar system, the most likely culprits would have been the giant planets themselves, particularly Neptune, whose gravitational influence dominates that entire region. As Neptune migrated outward from the Sun during the solar system's formation, its immense gravity would have acted like a colossal plow, scattering countless icy bodies into new and often highly inclined orbits. It's entirely possible that a young Orcus had a close encounter with Neptune and was flung onto its current path. This is a standard story for many scattered disk objects, but Orcus's perfectly stable resonance with Neptune complicates this neat explanation. How could it have been violently scattered into a high-inclination orbit while simultaneously locking into such a delicate and precise gravitational dance? It's a bit like being thrown from a moving car only to find yourself perfectly pacing it a mile away. The two events seem contradictory. This inconsistency forces astronomers to consider even more dramatic possibilities. Perhaps the gravitational disturbance didn't come from a known planet at all, but from something we can no longer see. One compelling theory is the existence of a yet undiscovered planetary mass object, often referred to as Planet 9 or Planet X, lurking in the extreme outer solar system. The gravitational tug from such a massive world, on a distant and elongated orbit of its own, could have gradually perturbed Orcus's path over billions of years, slowly raising its inclination without completely disrupting its resonant relationship with Neptune. Orcus, in this scenario, would be a clue, a piece of celestial evidence pointing toward the existence of a much larger hidden world. Another fascinating idea points to a time when the solar system was far more crowded. Orcus's inclined orbit might not be the work of a single giant, but the cumulative effect of many smaller gravitational jostles. In the earliest era, the Kuiper Belt was likely packed with thousands of Pluto-sized objects, a bustling community of large worlds that has since been mostly cleared out by gravitational scattering and collisions. A series of close passes with several of these large primordial bodies could have just as effectively nudged Orcus into its current tilted state. This would mean its orbit is a fossilized relic of a lost population, a time capsule from an epoch when the outer solar system was a completely different and far more dynamic place than it is today. Each theory offers a different glimpse into the violent processes that shaped our cosmic neighborhood, and Orcus, with its strangely angled path, holds the key to understanding which of these dramatic stories is true. While the unusual orbit of Orcus tells a story of gravitational drama, a closer look at the system itself reveals a visual paradox that stands as our eighth great mystery: the stark color dichotomy between Orcus and its moon, Vanth. When we point our most powerful telescopes toward this distant pair, we don't see two matching worlds. Instead, we see a study in contrasts. The dwarf planet Orcus itself presents a largely neutral, grayish-white appearance, much like freshly fallen snow. Its moon Vanth, however, shines with a distinctly reddish hue, a color more commonly associated with the very oldest and most organic, rich surfaces in the outer solar system. This isn't a minor difference in shading. It's a fundamental divergence in color that suggests these two closely bound objects have lived two very different lives. This color split is a profound clue about the composition and history of each body. The neutral, bright white of Orcus strongly supports the idea of a surface frequently renewed by relatively clean water ice, likely from the cryovolcanic activity we discussed earlier. This process effectively gives the world a periodic facelift, covering up any darker, redder materials that might have accumulated over time with a fresh, brilliant frost. Vanth's persistent red color, however, tells the opposite story. Its surface appears ancient and unrenovated, left exposed to the harsh environment of space for eons. The reddening is a well-understood process called space weathering, where cosmic radiation and solar wind bombard exposed ice and simple organic compounds, slowly baking them into a complex, dark red material known as tholins. Vanth's ruddy complexion suggests it has been a silent witness to this process for billions of years, its surface untouched by any internal geological activity that could refresh it. The most immediate question this raises is a simple one. If these two objects formed together from the same cloud of material, shouldn't they share the same basic color? Their divergent appearances challenge the simplest version of the co-formation theory. It suggests that while they may have been born from the same event, their subsequent histories diverge dramatically. Perhaps Vanth, being smaller, lost its internal heat source much more quickly than its larger parent. Without any internal engine to drive geological change, its surface froze solid and began to slowly redden under the relentless rain of radiation, while Orcus continued its occasional icy resurfacing, maintaining its brighter, cleaner look. Another possibility is that the giant impact theory of formation could naturally lead to this color difference. The colossal collision that might have created Vanth could have blasted material from deep within a differentiated Orcus onto the surface of the new moon. If Orcus had already separated into a rocky core and an icy mantle, the impact could have ejected a mixture of this dark, rocky core material and ice, creating a moon with a fundamentally different surface composition from its icy parent from the very beginning. Vanth's redness in this scenario wouldn't just be a sign of age, it would be a sign of its birth, a permanent stain from the deep interior of its progenitor. A third and perhaps most intriguing idea is that Vanth was indeed captured, and its red color is a relic of its origins in a completely different part of the early Kuiper Belt. The outer solar system wasn't a uniform mixture. It likely had compositional gradients with different materials dominating at different distances from the Sun. A reddish object like Vanth could have formed much further out, in a region where more volatile and organic rich ices were common. It then could have migrated inward, eventually being gravitationally captured by Orcus. This would make them not siblings, but strangers that found each other, their color difference a permanent record of their distinct birthplaces. The silent, contrasting hues of this binary pair are more than just a visual curiosity. They are a deep, layered record of formation, evolution, and perhaps even cosmic immigration, waiting patiently in the dark for us to decipher their meaning. While the contrasting colors of Orcus and Vanth paint a picture of divergent histories, the fundamental motion of the dwarf planet itself presents another layer of intrigue. Our ninth great mystery focuses on the rhythm of Orcus's spin, or more accurately, its lack of speed. For an object of its size and location, Orcus rotates at a surprisingly slow and leisurely pace. Its day, the time it takes to complete a single full turn on its axis, lasts just over 10 hours. This might not sound particularly slow. After all, an Earth day is 24 hours, but in the context of similar Kuiper Belt objects, it is an outlier. Many of its icy cousins, similar in size and composition, are whirling much faster, completing a rotation in mere handfuls of hours. This sluggish spin is a significant anomaly, a clue that something or someone has been applying the brakes. In the physics of our solar system, an object's rotation is a conserved record of its formation. The initial spin is imparted by the chaotic collisions and accretion of countless smaller bodies, and without any external influence, that spin rate remains largely constant for billions of years. A fast rotator typically indicates a history free from major disruptive events, while a slow spin often points to a specific interfering force. For Orcus, the most obvious and compelling suspect is its massive companion, Vanth. The gravitational pull between a planet and its moon doesn't just govern their orbits, it can also create a phenomenon known as tidal locking, where the gravitational tug slows the rotation of the larger body until it is synchronized with the moon's orbit. We see this perfectly with our own moon, which turns once on its axis in the exact same time it takes to orbit Earth, forever showing us the same face. The situation with Orcus and Vanth appears to be a textbook case of this process in its final stages. Current observations strongly suggest that the two bodies are mutually tidally locked. This means they perpetually face each other with the same hemispheres locked in a silent, eternal gaze across the void. For this delicate balance to have been achieved, Vanth's substantial gravitational influence must have been steadily working against Orcus's original rotation for eons, gradually sapping its angular momentum and slowing its spin down to its current synchronized crawl. This process acts as a cosmic brake pad, and the 10-hour day we observe now is the end result, the telltale sign of a gravitational relationship that has matured over the immense age of the solar system. Yet, this elegant explanation isn't without its complications. The process of tidal locking is most efficient when the two bodies are relatively close together. While Vanth is large, its orbit around Orcus is actually quite wide. This greater distance means its gravitational braking power would be significantly weaker, making the process of slowing Orcus's spin far less efficient and requiring a truly staggering amount of time. This leads to a fascinating dilemma. Has the Orcus-Vanth system simply existed, unchanged and interacting, for nearly the entire 4.5 billion year history of the solar system to achieve this lock? Or was Orcus's initial rotation rate even slower than we can easily explain, making the journey to tidal locking a much shorter trip? This opens the door to alternative theories about its formation. Perhaps Orcus never was a fast spinner to begin with. If it formed from a relatively gentle, low-energy accretion of material in its specific region of the primordial disk, it might have started life with a very slow rotation, making the path to tidal locking with Vanth a much more straightforward affair. Its current spin rate wouldn't be the result of braking, but rather a preserved relic of its birth conditions. The mystery of its slow rotation, therefore, becomes a dual question. Is it a story of gravitational influence or a story of primordial origin? The answer likely holds critical details about the environment in which this distant duo first came to be, providing a unique window into the physical conditions of the early Kuiper Belt and the dynamic processes that shape the orbits and spins of the countless worlds within it. Even as we ponder the slow spin of Orcus, our attention is drawn to an even more elusive feature: the possibility that this distant world might, however briefly, hold onto a shroud of gas. The 10th great mystery confronting scientists is the tantalizing evidence for a transient atmosphere. The very idea seems to defy logic. At its immense distance, the sun's warmth is a mere whisper, far too feeble to sublimate ices directly from solid to gas on any permanent basis. Yet the clues suggest that when Orcus reaches the closest point in its elongated orbit, a subtle transformation may occur. The slight increase in solar energy could be just enough to trigger the most volatile ices on its surface, like nitrogen, methane, or carbon monoxide, to vaporize, creating a tenuous and temporary envelope of gas that clings to the dwarf planet for a short, glorious season before freezing back onto the surface as it journeys back into the deep freeze. Detecting such a fleeting atmosphere is a monumental challenge that pushes our observational capabilities to their absolute limit. unlike Pluto, which has a persistent though thin atmosphere, any gaseous layer around Orcus would be exceptionally weak and confined, likely only a few microbars thick, a pressure millions of times less than that at sea level on Earth. Our best chance to spot it comes during a stellar occultation, a celestial event where Orcus passes directly in front of a distant star. As the starlight winks out, scientists can analyze its light for tiny, telltale distortions. If an atmosphere is present, the light will dim in a very specific, gradual way instead of snapping off abruptly, providing a ghostly signature of the intervening gases. So far, the results have been ambiguous. Some data hints at a slight, gradual dimming, while other observations show a sharp cutoff. This inconsistency only deepens the enigma, suggesting the atmosphere may come and go in a cycle we have not yet fully mapped. The dynamic nature of such an atmosphere adds a whole new layer of complexity to understanding this world. It would mean Orcus is not a static, frozen statue, but a seasonally active body, breathing out a faint exhalation of gas before drawing it back in. This process would continually reshape its surface in subtle ways. As the ices sublimate, they would leave behind a lag deposit of darker, dustier material, concentrating it in certain areas. Then, when the atmosphere collapses and refreezes, that frost might not settle back uniformly, potentially creating the very patchwork of bright and dark terrain we find so puzzling. This would turn the surface into a chemical record of its atmospheric cycles, a kind of frosty journal documenting its repeated, seasonal attempts to become a more active world. Finding definitive proof of this transient shroud would fundamentally alter our perception of objects in the Kuiper Belt. It would place Orcus in a special category of dynamically active icy worlds, alongside others like Pluto, that undergo seasonal changes and possess a complexity we are only beginning to appreciate. The presence of even a temporary atmosphere implies a delicate and ongoing geochemical cycle, where materials are constantly exchanged between the surface and the space immediately above it. This isn't just a simple ball of ice, it's a world with weather, albeit on a scale and time span almost incomprehensible to us. The hunt for this ethereal atmosphere continues, a painstaking effort to capture the ghost of a breath from a world 4 billion miles away. Moving from the ethereal possibility of an atmosphere, we plunge deep beneath the surface to confront a mystery rooted in the very core of this world. Our 11th great mystery is a fundamental puzzle of mass and volume, the density discrepancy of Orcus. By measuring how its gravity influences the orbit of its moon Vanth, astronomers can calculate the system's total mass. Combining this with estimates of its size from direct imaging gives us its average density. This number is more than just a statistic, it's a crucial clue to what this dwarf planet is made of. The calculated density sits in a frustrating gray zone lower than that of pure rock, confirming it must be a mix of rock and ice, but not quite matching the precise ratios we'd predict for a standard, undifferentiated Kuiper Belt object. This slight mismatch between prediction and reality is a classic scientific clue, a sign that our simple models are missing a key piece of the puzzle. If Orcus were a homogeneous ball of mixed rock and ice, its density should fall within a fairly predictable range. The fact that it doesn't forces us to consider that its interior is not a uniform blend. Instead, the materials have likely sorted themselves out, a process known as differentiation. This is what happens when an object contains enough internal heat, whether from its formation or radioactive decay, to melt. The heavier, denser rocky material sinks inward to form a central core, while the lighter, buoyant ices rise to form a mantle and crust. This separation changes the object's overall density profile dramatically. The most thrilling possibility emerging from this density puzzle is the potential for a hidden, liquid subsurface ocean locked away beneath the frozen crust. We know that mixtures of water ice with other compounds like ammonia or salts can dramatically lower the freezing point, creating a potent antifreeze effect. If the rocky core of Orcus is still warm from the decay of radioactive elements, that heat could be sufficient to maintain a layer of this slushy, liquid brine between the solid core and the solid icy shell above. The presence of such an ocean would perfectly explain the density measurements, as it would create an internal structure less dense than a completely solid rock-ice mixture. This isn't mere speculation. We see evidence for such oceans on other distant moons like Enceladus and Europa, proving that liquid water can persist in the most unexpected places. This idea of a warm interior powered by radioactivity is compelling, but it faces a significant hurdle: size. Orcus is smaller than Pluto or Europa, bodies for which subsurface oceans are more confidently proposed. A smaller object loses its internal heat to the frigid vacuum of space much more rapidly. For Orcus to still possess enough heat to maintain even a slushy ocean, its interior would need to be exceptionally well insulated, perhaps by a thick, blanketing mantle of ice, or it would require a higher than expected concentration of radioactive elements in its core. Alternatively, the gravitational tug-of-war with Vanth could provide an extra energy source through tidal heating, flexing the interior and generating warmth through friction, though the Moon's wide orbit makes this effect likely minimal. The density discrepancy, therefore, isn't just a number. It's a direct challenge to our understanding of thermal evolution, forcing us to ask how a modest-sized world can possibly retain the heat necessary to power such a dynamic interior billions of years after its formation. The implications of a subsurface ocean are, of course, profound. It would instantly elevate Orcus from a frozen fossil to a potentially habitable environment. Where there is liquid water, chemical energy, and a stable environment, the conditions for life, as we understand it, could theoretically exist. While finding life there remains a distant and speculative dream, the mere possibility reshapes our search for biology in the solar system, expanding it to include these dark, distant dwarf planets. The unresolved density of Orcus is far more than an academic curiosity. It is a measurement that points toward hidden depths and fantastic possibilities, a single number that hints at a warm, wet, and utterly mysterious heart beating in the perpetual cold. The name we give a world often carries a weight of expectation, and for our 12th mystery, we find a deeply resonant connection between the ancient and the modern. This distant dwarf planet was not named at random. It was deliberately christened Orcus after the Etruscan and later Roman god of the underworld, a punisher of broken oaths who presided over the domain of the dead. At first glance, this seems like a fittingly dark name for an object so far from the sun's light, eternally locked in the deep freeze of space. But the true intrigue lies in how unnervingly accurate this mythological name has become, as if the ancients somehow foreshadowed the bizarre characteristics modern science would uncover. Think about the underworld of myth. It wasn't merely a place of death, but a hidden realm with its own strange geography, its own rules, and its own silent, powerful currents flowing beneath a static surface. This is a near-perfect description of the modern Orcus. Our observations suggest it may be a geologically active world, potentially hiding a liquid ocean beneath its crust, a hidden, subsurface realm of its own. Its perfectly synchronized orbit with Neptune and its gravitational grip on its moon, Vanth, represent the unbreakable oaths and binding punishments of its namesake, a system locked in a celestial contract for eons. Even its patchy surface of bright ice and dark material mirrors the mythological conception of the underworld as a place of stark contrasts, of judgment and reward, of light and shadow. The name is more than a label. It's a prophecy etched in myth that science is slowly bringing to light. This alignment between an ancient deity and a modern astronomical discovery invites a fascinating reflection on the human impulse to map our stories onto the cosmos. Long before we had telescopes, we used mythology to explain the world's mysteries, personifying the unknown forces of nature. In naming this object Orcus, astronomers have unconsciously continued that tradition, linking our oldest stories to our newest frontiers. It creates a beautiful, almost poetic continuity in our quest for understanding, bridging the gap between the storytellers of old who looked up at the night sky with wonder and the scientists of today who peer into the data with powerful instruments. The name Orcus, therefore, does more than just identify a ball of ice. It enriches it, embedding this cold, distant world into a much larger human narrative of exploration, fear, and fascination with what lies in the darkness. But the gravitational influence of a world like Orcus may extend far beyond its immediate partnership with Vanth, leading us directly into our 13th great mystery, its subtle but potentially profound interaction with other inhabitants of the Kuiper Belt. Out in that vast, dark expanse, countless icy bodies drift on their own lonely paths, and the gravitational pull of every single object, no matter how small, tugs on all the others in an impossibly complex web of influence. Orcus, as one of the larger denizens of this region, is not just a passive traveler on its own set path. It acts as a minor gravitational shepherd, its presence subtly sculpting the orbits of smaller objects that drift too close over immense spans of time. This role as a local gravitational pivot is a key piece of the puzzle in understanding the present-day structure of the Kuiper Belt. Computer simulations of the solar system's evolution often rely on the known masses of the major planets to model how smaller objects should be distributed. Yet, there are peculiar gaps and unexpected clusters of objects in certain orbital resonances that these models struggle to explain. The collective gravitational influence of larger dwarf planets like Orcus, Pluto, and Haumea could be the missing factor. Their combined mass, once accounted for, might resolve these orbital anomalies, effectively filling in the gaps of our gravitational maps of the outer solar system. Orcus, therefore, isn't just a subject of study. It's an active participant in shaping the environment around it, its gravity helping to herd smaller Kuiper Belt objects into the patterns we observe today. The most tantalizing possibility arising from these interactions is the hint of something even larger at play. Some of the most distant and strangely clustered orbits of extreme Kuiper Belt objects have led scientists to propose the existence of a so-called Planet 9, a hypothetical world several times the mass of Earth orbiting far beyond Neptune. The gravitational pull of such a massive object would be the dominant force organizing these distant orbits. Intriguingly, the orbital parameters proposed for this unseen planet share certain resonant harmonies with the orbit of Orcus itself. This raises a fascinating question. Could Orcus's path be not just a product of its past with Neptune, but also subtly influenced by this potential distant giant? It might be acting as a local proxy, its own gravitational effects on smaller objects amplifying or reflecting the larger scale orchestration being conducted from much, much further away. In this way, studying the minor orbital disturbances caused by Orcus could provide indirect but crucial evidence for the existence of a massive world we have yet to lay eyes on. Beyond these contemporary interactions, the very path that Orcus walks today might be a ghostly echo of a much more violent and crowded past. The early Kuiper Belt was not the sparse region it is now. It was likely packed with thousands of Pluto-sized objects and countless more smaller bodies. In such a bustling environment, close gravitational encounters were commonplace. The current orbital inclination of Orcus, its tilt relative to the solar system's plane, could be the permanent scar from a glancing blow with another large primordial body billions of years ago, an encounter that knocked it into its present elevated path. Furthermore, the very existence of its large moon, Vanth, points to a tremendous historical collision. The debris from such an impact wouldn't have just formed the moon. It would have scattered a cloud of smaller fragments across the region, potentially seeding the neighborhood with a family of objects that still share similar orbital characteristics. Finding and identifying such a collisional family with Orcus at its center would be like finding pieces of a shattered celestial vase, allowing us to reassemble the moment of a defining event in the deep history of the solar system. Every small object whose path is gently shepherded by Orcus today could be a silent sibling, a remnant of the chaotic and dynamic processes that built the outer solar system as we know it. Our 14th mystery invites us to consider Orcus not as a static portrait, but as a dynamic film, watching how its appearance changes over months and years. Astronomers tracking this distant world have documented subtle but undeniable fluctuations in its overall brightness. These aren't the predictable dimmings and brightenings caused by its rotation, which would repeat in a steady, reliable rhythm. Instead, these are longer-term variations in its total reflectivity, a flickering that suggests something on or around Orcus is changing in a way we can't yet fully explain, adding another layer of intrigue to this already puzzling world. One compelling explanation points to the possibility of seasonal shifts on a world without traditional seasons. As Orcus travels along its markedly elliptical orbit, its distance from the Sun varies by hundreds of millions of miles. When it reaches perihelion, its closest approach, the slightly more intense solar radiation might be sufficient to trigger the sublimation of the most volatile ices on its surface, like nitrogen or methane. This process would expose a darker, more ancient layer of material underneath, causing the world as a whole to appear slightly dimmer from our vantage point. Then, as it journeys back to the colder reaches of its orbit, these gases could recondense as a fresh, bright frost, increasing its overall reflectivity once more. This would create a slow, multi-decadal cycle of brightening and darkening tied directly to its long year, a seasonal heartbeat measured in centuries rather than months. Another fascinating possibility involves the very geology of the surface itself. If cryovolcanism is indeed active on Orcus, it would not be a constant process. These icy eruptions would likely be sporadic events occurring at irregular intervals. A significant eruption would coat a vast area in brilliant, fresh ice, causing a notable, sustained increase in the world's overall brightness that would last until space weathering began to darken the new surface. The observed fluctuations could therefore be a direct record of this episodic resurfacing, a log of eruptions written in light across the face of the dwarf planet. We would be essentially watching its geological activity in ultra-slow motion, with each change in brightness marking a new chapter in its hidden volcanic history. We must also look beyond Orcus itself to the environment through which it travels. The Kuiper Belt is not a perfect vacuum. It is filled with tenuous clouds of fine dust and debris, remnants of countless microscopic collisions over billions of years. If Orcus were to pass through a slightly denser patch of this cosmic haze, the effect could be twofold. First, the dust itself could slightly obscure our view, making the object appear momentarily dimmer. More intriguingly, this interplanetary dust could be settling onto the surface of Orcus, particularly on its brighter, icy plains, creating a dark, thin film that reduces its reflectivity. A later increase in brightness could then be explained by a fresh cryovolcanic flow or a seasonal frost covering that dark dust layer, effectively cleaning the surface and restoring its shine. This would make its brightness variations a measure not just of its own activity, but of the clumpy and uneven nature of the space it inhabits. Untangling the precise cause of these flickers is a monumental challenge that requires patience and long-term observation. Astronomers must meticulously measure its brightness over decades, carefully subtracting the well-understood effects of its rotation and its changing distance from both the Sun and Earth. The residual, unexplained variation is the signal we're looking for, the whisper of activity. Each tiny dip or peak in the light curve is a data point in a cosmic mystery, a clue that is helping us determine whether we're seeing the effect of seasons, volcanoes, or the dusty environment of the outer solar system. This meticulous photometric detective work transforms Orcus from a frozen snapshot into a moving picture, revealing a world that is far from static and continues to evolve in the deep, silent dark. Given its substantial size and the presence of its large moon Vanth, it seems almost natural to wonder if Orcus might host an entire family of smaller satellites. This leads us to our 15th great mystery, the puzzling absence of any additional moons. Despite exhaustive searches using our most powerful telescopes, not a single other moon has been definitively confirmed orbiting this dwarf planet. This isn't for lack of trying. Astronomers have scanned the space around it with extreme sensitivity, looking for the faint glint of sunlight off even the tiniest of companions. The fact that they've found nothing is, in itself, a highly significant and somewhat unexpected result that forces us to reconsider how this binary system came to be. In the context of other similar systems, this cleanliness is unusual. Look at Pluto, for instance, which has 4 smaller moons, Styx, Nix, Kerberos, and Hydra, orbiting alongside its major partner, Charon. These are believed to be leftover debris from the giant impact that created the entire system. If a similar colossal collision gave birth to Vanth, we would reasonably expect to find a similar retinue of smaller fragments, a cloud of debris that either coalesced into additional moons or remained as a faint ring of dust. The pristine, uncluttered space around Orcus and Vanth suggests no such debris field exists, which presents a major complication for the giant impact theory. It implies that if there was a collision, it was an extraordinarily clean and efficient one, somehow leaving behind only one large secondary body and virtually no other detectable fragments, a scenario that pushes the limits of our computer simulations of such violent events. This absence of smaller moons also influences our understanding of the system's long-term stability. Small moons are often vulnerable to gravitational perturbations. They can be ejected from orbit entirely by the complex gravitational interplay between the primary planet and its largest moon, or their orbits can become so unstable that they eventually collide with one of the larger bodies. The fact that no small moons have survived, if they ever existed, tells us that the gravitational environment around Orcus and Vanth may have been too chaotic to allow them to persist. Their current peaceful, tidally locked embrace might be the serene end result of a much more turbulent and dynamic past that cleared the neighborhood of any smaller siblings. The possibility of very small or dark moons, however, can't be entirely ruled out. Our current technology has its limits. A moonlet made of very dark material, or one that is simply too small, perhaps only a kilometer or 2 across, could easily evade detection from 4 billion miles away. A future close-up mission could fly through the space around Orcus and discover a handful of these tiny, elusive worlds, and that discovery would immediately resolve the mystery. It would align the system's formation story more closely with that of Pluto and other collisional families, providing the missing debris we'd expect. Their continued absence, however, makes the Orcus-Vanth pair an even more unique and enigmatic binary, a pristine duo whose clean partnership stands out in a solar system often filled with celestial crowds. These unexplained spectral signatures form our 16th great mystery, a chemical puzzle written in the faint light reflected from Orcus's surface. When astronomers break down this light into its constituent colors, creating a spectrum, they are essentially reading a unique barcode that reveals the chemical identity of the materials present. For most objects in the solar system, this spectrum shows familiar absorption lines that correspond to well-known ices like water or methane, or perhaps common silicates. Orcus, however, reveals a different story. Its spectral data contains distinct and persistent features that stubbornly refuse to match any compound in our extensive databases of ices, minerals, or complex organics. It's as if we're trying to read a book written in an alphabet we've never seen before, a clear signal that the surface chemistry of this world is far more exotic than we ever anticipated. The immediate implication is that we are likely seeing the spectral fingerprints of materials that are either entirely new to science or exist in a state or combination we have not yet been able to replicate in a laboratory. The extreme conditions on Orcus, the near absolute zero temperatures, the intense cosmic radiation, and the crushing vacuum create a unique environment for chemistry that is impossible to fully simulate on Earth. Over billions of years, this environment could be cooking up novel compounds. One strong possibility is the existence of complex crystalline structures within the ice itself. Water ice isn't just a simple solid. It can form numerous different crystalline phases depending on temperature and pressure. The peculiar conditions in the Kuiper Belt might foster the formation of an exotic, metastable phase of ice that has a spectral signature we simply haven't catalogued yet. Another fascinating avenue involves the interaction between the known ices and the constant barrage of high-energy radiation. Cosmic rays and solar wind particles slamming into the surface could be breaking apart simple molecules and driving a process called radiolysis, forcing the fragments to recombine into longer, more complex, and entirely unknown polymer chains. This could create a class of reddish organic compounds even more complex than the tholins we see on other worlds, with a unique spectral signature specific to Orcus's particular blend of initial ices and its exposure history. The dark, unidentified material mixed with its bright ice could be the very source of these mysterious spectral lines, a tar-like substance that is the end product of this relentless cosmic irradiation. The composition of the original building blocks that formed Orcus also comes into question. The solar system is not chemically uniform. It formed from a cloud of gas and dust that likely had regional variations in composition. Orcus may have accreted from a pocket of the primordial nebula that was particularly rich in a specific element or compound that is rare elsewhere. This unique starting ingredient, now baked into its surface, could be responsible for the strange spectral features. We might be looking at the preserved chemistry of a distinct region of the early solar system, a recipe that was used nowhere else, making Orcus a one-of-a-kind chemical repository. These unexplained lines in its spectrum are therefore more than just a curiosity. They are a direct challenge to our understanding of cosmic chemistry, pointing toward processes and compounds that await discovery in the frozen laboratory of the outer solar system. This brings us to a fascinating celestial mirror image, our 17th mystery, the uncanny and deliberate comparison between Orcus and Pluto. In many ways, Orcus seems to be a dark reflection of its more famous cousin, so much so that it has earned the nickname the Anti-Pluto. Both are substantial dwarf planets residing in the Kuiper Belt. Both are locked in a stable orbital resonance with Neptune. Pluto completes 2 orbits for every 3 of Neptune's, while Orcus completes 3 orbits for every 2 of Neptune's, a perfect inverse relationship. Both possess large, singular moons, Charon for Pluto, Vanth for Orcus, that dominate their gravitational systems, and both show tantalizing hints of geological activity and surface renewal on worlds that should be frozen solid. They are, in a gravitational and structural sense, cosmic twins. Yet, for all their similarities, the differences between them are where the true mystery lies, highlighting how 2 objects following similar cosmic blueprints can evolve into such distinct worlds. The most striking difference is one of sheer scale and composition. Pluto is the king of the Kuiper Belt, significantly larger and more massive than Orcus. This greater size has allowed Pluto to retain internal heat far more effectively, powering a stunningly diverse and active geology that includes vast nitrogen ice plains, towering water ice mountains, and a likely subsurface ocean. Orcus, while potentially active, appears to be a quieter, more subdued world. Its activity is hinted at through subtle clues like bright patches and thermal anomalies, whereas Pluto's drama is written across its surface in bold, unambiguous features. This difference in vitality is a direct consequence of their size. a demonstration of how a relatively small change in mass can lead to a dramatic divergence in geological destiny. Their surfaces tell another story of divergence. Pluto's landscape is a complex palette of colors, from the rusty red of tholin-rich regions to the stark white of nitrogen ice. Its atmosphere, though thin, is persistent and creates hazy layers and winds that shape the surface. Orcus, by contrast, presents a more monochrome and cryptic face. Its brighter, more neutral tones and the stubborn mystery of its dark materials suggest a different chemical history, one potentially lacking the very volatile ices like nitrogen that so dominate Pluto's geology and create its atmosphere. Orcus might be a world where water ice is the dominant geological actor, whereas Pluto is a world of more exotic and volatile ices. This makes Orcus a crucial control subject. By studying what it lacks compared to Pluto, we can better understand the unique conditions that made Pluto the complex world it is. This comparison forces a profound question about the nature of the Kuiper Belt itself. We once thought of it as a relatively uniform repository of ancient, primitive ice balls. The stark differences between Orcus and Pluto shatter that simplistic view. They reveal the Kuiper Belt to be a region of immense diversity, where objects of similar size, formation era, and orbital dynamics can follow wildly different evolutionary paths based on their specific composition, internal heat, and perhaps even their unique collision histories. Orcus isn't just a smaller, fainter copy of Pluto. It is its own unique entity, a world that chose a different path billions of years ago. Understanding why these twin-like objects grew into such different adults is key to mapping the full spectrum of possibilities for icy dwarf planets, not just in our solar system, but around other stars as well. The anti-Pluto nickname, therefore, isn't just a clever moniker. It's a scientific imperative reminding us that to truly understand one of these distant worlds, we must always seek out and study its opposite. Venturing beyond the immediate pull of its own gravity and the faint whisper of a potential atmosphere, we find Orcus subjected to another, far more relentless force, the ceaseless stream of charged particles ejected from the Sun. This introduces our 18th great mystery, the unique and potentially transformative influence of the solar wind on this distant world. Unlike the gentle pressure of sunlight, the solar wind is a supersonic plasma of protons and electrons, a corrosive spray that bathes every object in the solar system. At Orcus's immense distance, this wind is vastly weaker than what we experience closer to the Sun, but its effects, acting over billions of years, could be the invisible sculptor behind some of the most perplexing features we observe. The primary mechanism at work here is a process called sputtering. When these high-energy particles from the solar wind slam into the surface ice of Orcus, they don't just bounce off. They transfer their energy, literally knocking individual water molecules and other atoms right out of the surface and into the void. This is a form of erosion on an atomic scale, a slow-motion sandblasting that could gradually darken and redden the surface by selectively removing lighter molecules and leaving behind a more concentrated layer of dark, carbon-rich material. This same process is believed to be responsible for the dark red hue of many other Kuiper Belt objects, yet Orcus, with its unusually bright patches, appears to be actively resisting it. This presents a fascinating contradiction. Why does one of the brightest objects in the region seem so resilient to the very force that darkens its neighbors? One compelling theory suggests that Orcus's surface is simply being replenished faster than the solar wind can weather it. If cryovolcanic eruptions are indeed periodically laying down fresh, bright layers of ice, they are effectively erasing the darkening work of the solar wind almost as soon as it begins. In this scenario, the bright regions are not areas that have avoided sputtering. They are simply the most recently resurfaced areas, their brilliant frost not yet having had enough time to be processed by the relentless particle rain. The solar wind's influence becomes part of a dynamic cycle, not a one-way process toward darkness, and its effectiveness becomes a direct measure of the interval between resurfacing events. The solar wind might also be a key player in creating the mysterious chemical signatures we can't yet identify. Beyond mere physical erosion, the intense energy of these particles can break apart stable molecules on the surface, driving a complex and poorly understood type of space chemistry known as radiolysis. This could be transforming simple ices into new, more complex compounds right there on the surface. The unidentified dark material mixed with Orcus's water ice could be the end product of this radiolytic processing, a complex tar of newly forged organic molecules whose spectral signature is unique simply because the specific blend of ices on Orcus, combined with its particular exposure history, is a combination not found anywhere else. The solar wind, in this light, isn't just a destructive force, it's a bizarre kind of alchemist, tirelessly working to transmute the surface of Orcus into something entirely new. Furthermore, the very weakness of the solar wind at this distance might be creating unexpectedly complex results. With lower particle energies, the sputtering and radiolysis processes may operate at a much slower, more methodical pace, allowing for the formation of intermediate chemical compounds that would be instantly destroyed by the more intense wind closer to the Sun. Orcus could be a unique laboratory for studying low-energy plasma surface interactions, a place where chemistry unfolds in a way we cannot replicate on Earth. The subtle and unexplained differences between its surface and that of other Kuiper Belt objects may not be due to a lack of solar wind influence, but rather a testament to its peculiar and patient effects in the profound quiet of the outer solar system. This very modern discovery of such a substantial world opens our 19th great mystery, the historical gap in our observations. How did an object as significant as Orcus, a dwarf planet rivaling Pluto's moon Charon in size, manage to evade detection for so long, only revealing itself to science in the 21st century? The answer isn't a simple tale of overlooked data. It's a story about the profound technological and logistical challenges of probing the solar system's deepest shadows, and a humbling reminder of how much of our own cosmic backyard remains unexplored. The primary reason for its late discovery lies in its immense distance and the limitations of past survey technology. Orcus orbits the Sun at an average distance of nearly 40 times that of Earth, a realm where sunlight is desperately faint. From that far away, it appears incredibly dim, a speck of light over 1 billion times fainter than what the unaided human eye can see. For most of astronomical history, our telescopes simply weren't powerful enough or sensitive enough to detect such a faint object against the black velvet of space. The photographic plates used throughout the 20th century lacked the fine-grained sensitivity of modern digital charge-coupled devices, or CCD. An object like Orcus would have left no discernible impression on those old emulsions, its light too weak to trigger a chemical reaction. It was effectively invisible to the tools of the era. Furthermore, its motion across the sky is agonizingly slow. It takes Orcus over 247 years to complete a single orbit, meaning its movement against the backdrop of fixed stars from one night to the next is almost imperceptible. The key technique for discovering distant solar system objects involves taking multiple images of the same patch of sky over several nights and looking for anything that has moved. In the days before automated, computerized analysis, this was a painstaking task done by human eyes, often comparing photographic plates by hand under a blink comparator, the very method Clyde Tombaugh used to find Pluto in 1930. An object moving as slowly as Orcus would have barely shifted its position between plates taken even weeks apart, making it far more likely to be dismissed as a static star or a flaw in the emulsion. Its glacial pace allowed it to perfectly mimic the background. The sheer vastness of the sky itself was another formidable obstacle. Astronomers couldn't simply point a telescope anywhere and hope to find something. They had to make educated guesses about where to look, and for much of history, the Kuiper Belt wasn't even a confirmed concept. Early surveys focused on the ecliptic, the narrow band in the sky where the planets travel. While Orcus does orbit near this plane, its significant 20-degree orbital inclination means it often strays well above and below the most intensely searched zones, taking it into celestial territories that were simply not prioritized by earlier, more limited searches. It was hiding in plain sight, but in a corner of the room nobody had thought to thoroughly check. The discovery of Orcus in 2004 was not a lucky accident. It was the direct result of a technological revolution. It was found by a team using the immense 48-inch Samuel Oskin telescope at Palomar Observatory, an instrument that was part of a new generation of wide-field surveys designed specifically to methodically scan the heavens for moving objects. This was coupled with the new power of CCD cameras, which are vastly more sensitive to light than photographic film, and sophisticated computer software that could automatically analyze the resulting digital images, detecting the subtlest shifts of even the slowest moving objects. Orcus was found because we finally built the eyes and the brains capable of seeing it. Its late arrival in our catalogues is a powerful testament to how technological leaps, not just theoretical insight, drive our exploration of the cosmos, continually revealing giants that were waiting silently in the dark all along. The idea of frigid volcanoes belching slush instead of lava might sound like pure science fiction, yet this very process may be the key to unlocking the most visible mysteries of Orcus. The evidence for this cryovolcanism is not something we can see directly, but is instead written in the world's starkly contrasting surface and its perplexing temperature readings. Those vast, brilliantly bright plains that stand alongside darker, ancient terrain are a powerful clue. On a world subjected to billions of years of relentless space weathering, such pristine, reflective ice should not exist. It should have been darkened long ago. The most logical explanation is that these areas have been recently, or at least periodically, resurfaced. Something is actively painting over the old, dark scars with a fresh, bright coat of frost, and cryovolcanism is the prime suspect for this celestial renovation. Envision not a fiery, explosive eruption, but a slow, oozing phenomenon. Deep within Orcus, residual heat from the decay of radioactive elements in its rocky core, or perhaps warmth generated by the gravitational flexing from its dance with Vanth, might be enough to maintain pockets of a liquid or slushy brine. This mixture, likely water fortified with ammonia or methanol acting as a powerful antifreeze, could be under immense pressure. Eventually, this frigid magma might find a weakness in the overlying icy crust, forcing its way up through fissures and fractures until it breaches the surface. There, in the airless void, it would instantly freeze, spreading across the landscape like a slow-moving glacier of new ice, filling in craters and creating the remarkably smooth, bright plains we infer from our observations. Each of these events would be a geological reset button, giving parts of Orcus a deceptively youthful appearance. What makes the possibility of this activity so surprising and frankly revolutionary is the extreme environment. Orcus exists in a perpetual deep freeze where surface temperatures hover near -240 degrees Celsius, a realm so cold that most geological processes we know on Earth should have ground to a halt billions of years ago. A small object this far from the sun should have lost its internal heat long ago, becoming an inert, frozen fossil. The mere suggestion that it might still be warm enough inside to melt ice and drive eruptions forces a complete re-evaluation of our models for these distant worlds. It implies that their interiors are far more complex and potentially better insulated than we ever imagined, perhaps by thick mantles of exotic ice that trap heat like a celestial thermos, or that tidal forces provide a non-negligible source of energy even at such vast distances. The implications of active cryovolcanism on Orcus would extend far beyond its own geology, reshaping our understanding of the entire Kuiper Belt. It would elevate these distant bodies from simple, primitive relics to dynamically active worlds with their own unique geological cycles. This opens the door to the even more thrilling possibility of a subsurface ocean. If enough heat is present to melt ice and drive it to the surface, it could certainly be enough to maintain a stable, liquid water ocean sandwiched between the rocky core and the solid icy shell above. Where there is liquid water, chemical energy, and a stable environment, the probiotic conditions for life, as we understand it, could theoretically exist. While finding life remains a distant dream, the confirmation of cryovolcanism on Orcus would make that dream feel suddenly, astonishingly, more plausible, suggesting that habitable environments may be hidden in the most remote and frigid corners of our solar system. This peculiar path and puzzling composition make Orcus far more than just a solitary curiosity. They provide a crucial independent check on our grandest theories of how the entire solar system was built. Orcus acts as a celestial historian, its very existence and properties serving as a test for the stories we tell about the violent, chaotic era of planetary migration that shaped our cosmic neighborhood billions of years ago. The most influential of these theories is the Nice model, named after the French city where it was developed. This model proposes that the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. Instead, they were born much closer together and subsequently migrated outward in a complex gravitational dance that scattered countless icy bodies throughout the outer solar system, creating structures like the Kuiper Belt and the scattered disk in a relatively short cataclysmic period. The orbit of Orcus is a key piece of evidence that supports this dramatic narrative, but it also adds a layer of subtle complexity that forces refinements to the model. Its stable 3-to-2 resonance with Neptune is a classic signature of an object that was gently shepherded into its current path during Neptune's outward migration, rather than being violently scattered. This suggests that the migration process wasn't entirely chaotic. It had a structured, almost orderly component that could capture and preserve objects in these stable gravitational harmonies. However, its unusually high orbital inclination presents a challenge. A perfectly smooth and steady migration might not easily produce such a pronounced tilt. This implies that the migration event itself may have been bumpier than we first thought, perhaps involving closer gravitational encounters between the giant planets or interactions with other large, since ejected bodies that provided the extra gravitational kick to lift objects like Orcus into their inclined orbits. The composition of Orcus adds another dimension to this historical puzzle. The apparent presence of abundant water ice, potentially overlying a differentiated interior with a rocky core, tells us that it must have formed early enough to incorporate short-lived radioactive isotopes like aluminum-26. The decay of these isotopes would have provided the necessary heat to melt its interior and separate rock from ice. This means Orcus is a primordial planetesimal, a surviving building block of the planets that coalesced in the very first few million years of the solar system's life. It isn't a later generation fragment, it's a genuine relic from the dawn of planetary formation. Its current location in the Kuiper Belt therefore wasn't its birthplace. It must have originated much closer to the Sun, in the region between the forming giants, and was then flung outward to its present distant orbit during the planetary migration described by the Nice model. It is a displaced immigrant holding onto the chemical signature of its warmer, inner system origins despite its long exile in the deep freeze. This makes Orcus a vital benchmark for understanding the composition of the primordial solar nebula at different distances from the Sun. By analyzing its surface ices and, potentially, the mysterious dark material that stains them, we are essentially conducting a geological survey on a sample that was forged near the birthplace of the giant planets and then transported to the outer darkness for preservation. Its chemistry is a time capsule, a record of conditions in a now-vanished part of the protoplanetary disk that was eventually incorporated into the cores of Uranus and Neptune. The unexplained spectral features that defy our current databases might be the key to identifying compounds that were common in that inner region, but are now extremely rare in the present-day Kuiper Belt. In this way, Orcus is not just an object that was moved by the Great Migration. It is a preserved piece of the very material that was being moved around, offering us a direct glimpse into the ingredients that were available for planet building 4.5 billion years ago. Its continued study is essential, for it forces our computer models of solar system formation to account for its specific, quirky details, moving us from a broad-brush narrative of planetary migration toward a far more precise and detailed understanding of our own cosmic origin story. But perhaps the most direct evidence for this hidden structure comes from a far more active form of investigation, leading us directly into our 22nd mystery: the unexplained and perplexing radar reflections bouncing back from this distant world. While we cannot yet send a dedicated radar beam to Orcus itself, powerful ground-based radar systems like the Arecibo Observatory before its collapse and the Goldstone Solar System radar have occasionally pinged the dwarf planet during its close approaches to other solar system objects. The echoes that return are not the simple, predictable reflections we would expect from a homogeneous ball of ice and rock. Instead, they are unusually bright and complex, carrying a signature that suggests the surface, or what lies just beneath it, is far more intricate than its outward appearance implies. These anomalous radar returns are a classic example of a scientific clue that is both tantalizing and deeply frustrating. The high reflectivity, or high radar albedo, indicates that the surface is an exceptionally efficient reflector of radio waves. On icy worlds, this is often a telltale sign of a very clean, cold, and coherent ice sheet, much like the ice sheets of Greenland or Antarctica that appear brilliantly bright on radar maps. However, this creates an immediate contradiction with our visual and spectroscopic observations, which show a surface contaminated with significant amounts of a dark, non-icy material. A surface littered with dark rubble or dust would typically scatter and absorb radar waves, producing a much dimmer echo. The fact that Orcus sends back such a strong signal suggests that the dark material we see is not distributed evenly across the surface, but might be concentrated in specific areas, leaving vast plains of exceptionally pure and transparent water ice that act like a cosmic mirror for radio waves. The complexity of the radar echo goes beyond mere brightness, however. The signal's polarization, the way the orientation of the radio waves is changed upon reflection, holds even more intriguing clues. Some of the returned signal shows a phenomenon known as the opposition effect, a sharp spike in brightness when the object is viewed with the radar beam hitting it directly head-on. This effect is commonly associated with very clean, porous surfaces, like freshly fallen snow or fine-grained ice crystals, where the radio waves can penetrate slightly before being reflected back, creating a coherent return. This supports the idea of those pristine icy plains, yet mixed within this are components of the signal that suggest a much rougher subsurface structure, perhaps layers of buried rock or pockets of different ices that scatter the radar in unexpected ways. The most thrilling interpretation of this data is that the radar waves are not just bouncing off the surface, they are penetrating it. A thick layer of exceptionally transparent water ice could allow the radar beam to pass through it and reflect off subsurface interfaces deeper within Orcus. The strange complexities in the signal could then be the echoes from buried geological features, the boundary between the icy crust and a slushy ocean beneath, the jagged top of a buried rocky core, or even layers of different ice types deposited by ancient cryovolcanic flows. This would mean the radar is giving us a ghostly sonogram of Orcus's internal structure, revealing a hidden world of complexity beneath a deceptively simple frozen shell. Each unusual spike and dip in the returned signal becomes a potential message from the dark, a hint of cliffs, valleys, and oceans we cannot see, waiting miles below the surface. Untangling this radar riddle is a monumental task that requires synthesizing all our other clues. The strong reflection aligns with the evidence for recent resurfacing and bright icy plains, while the signal's complexity dovetails with the density measurements that suggest a differentiated interior. It paints a picture of a world that is not just active on its surface, but richly layered beneath it, a frozen planet with a hidden geological heart that is only now beginning to send its faint, coded messages back to us across the billions of miles of empty space. The possibility of seasons on a world so far from the sun might sound like a contradiction, yet the elongated path of Orcus carves out a compelling case for cyclical change on a grand scale. Its orbit is not a neat circle but a pronounced ellipse, creating a dramatic difference in its distance from the Sun over the course of its 247-year-long year. At its closest approach, perihelion, it ventures to within 30 astronomical units, while at its most distant, aphelion, it retreats to nearly 48. This variation of over 18 astronomical units translates to a significant shift in the amount of solar energy reaching its surface. The difference in received sunlight between its closest and farthest point is a factor of more than 2.5. On a world where every photon of energy is precious, this is not a trivial fluctuation. It is the fundamental driver behind the hypothesis that Orcus may experience seasons, not of warmth and cold as we know them, but of sublimation and condensation, of atmospheric exhalation and icy inhalation. The proposed seasonal cycle would be a slow-motion ballet of frost and vacuum. As Orcus journeys inward toward perihelion, the slightly more intense solar radiation could provide just enough energy to trigger the sublimation of its most volatile surface ices. Imagine fields of nitrogen, methane, or carbon monoxide frost stable for decades, beginning to tremble at a molecular level, breaking their bonds and transforming directly from a solid into a tenuous gas. This process would create a transient, ultra-thin seasonal atmosphere, a momentary shroud that might last for decades as the dwarf planet rounds the sun. This gaseous envelope would not be uniform. It could create winds, however faint, and cause ices to migrate from warmer, sun-facing regions to colder, shadowed polar areas, much like the nitrogen glaciers on Pluto. The surface itself would change as the sublimation of these volatile ices leaves behind a lag deposit, a concentrated layer of the darker, less volatile dust and complex organics, potentially explaining the mysterious dark regions we observe. The seasonal hypothesis elegantly ties together several of Orcus's other puzzles into a single, cohesive narrative. The long-term brightness variations observed by astronomers could be a direct result of this cycle. As volatiles sublimate and darken the surface at perihelion, the world would appear dimmer. Then, as it journeys back into the deep freeze of aphelion, this feeble atmosphere would collapse, snowing back down onto the surface as a fresh, bright frost that increases its overall reflectivity. The puzzling thermal anomalies, those subtle warm spots, could be these very dark regions absorbing more solar energy during the warmer seasonal phase. Even the potential cryovolcanism might be indirectly tied to this, as the changing surface pressure from a temporary atmosphere could affect the stability of subsurface pockets of liquid, potentially triggering eruptions. In this model, the seasons are not a minor detail but the master clock regulating the geological and atmospheric activity of the entire world. Detecting these subtle seasonal shifts, however, remains one of the most formidable challenges in modern astronomy. The cycle is impossibly slow by human standards. A single season on Orcus lasts for well over half a century. We have only been aware of the world's existence for a tiny fraction of its orbital period, giving us only a single, frozen snapshot of its state. We are like a visitor arriving on Earth for one day and trying to comprehend the concept of autumn. Confirming the hypothesis requires patient, decades-long monitoring of its brightness, composition, and thermal emissions, looking for those gradual trends that align with its orbital position. The best opportunities come during stellar occultations, those rare moments when Orcus passes in front of a distant star. By analyzing how the starlight fades, scientists can hunt for the telltale gradual dimming that would indicate the presence of even a micron-thin atmosphere, the ghostly breath of a distant world summer. Each successful observation adds a crucial data point, slowly weaving together the story of a world that breathes once every 2.5 centuries. The gravitational symphony between Orcus and Neptune is not a solitary duet. It is part of a vast, unseen orchestra of resonant objects, each moving in precise harmony with the giant ice planet. This network of synchronized worlds forms our 24th great mystery, a celestial collective whose shared rhythms may hold the key to unlocking the deepest secrets of the solar system's turbulent youth. Orcus is not merely an isolated oddity. It is a prominent member of a specific class of trans-Neptunian objects known as Plutinos, all of which share its same 3:2 orbital resonance with Neptune. This means that for every 3 trips these distant bodies make around the Sun, Neptune completes exactly 2, a gravitational lockstep that has persisted for billions of years. The existence of this entire population is a monumental clue, a fossilized record of Neptune's epic migration during the solar system's formative chaos. The prevailing NICE model of planetary formation suggests the giant planets were not born in their current positions but shifted outward, their immense gravity scattering countless icy planetesimals in their wake. As Neptune moved, its gravitational influence acted like a net, capturing and corralling a specific family of objects into these stable resonant orbits. The Plutinos, including Orcus, are the captured remnants of that ancient upheaval, their very presence confirming a dynamic and violent restructuring of the outer solar system. They are not in their original birthplaces, they are immigrants shepherded into a specific neighborhood by the migrating giant. Studying Orcus in the context of its resonant siblings allows for powerful comparative planetology. While all Plutinos share the same orbital period and resonance, they exhibit a stunning diversity in size, color, composition, and even the presence of moons. Some, like Pluto, are large and complex with multiple satellites and a hazy atmosphere. Others are smaller, darker, and seemingly inert. Orcus sits intriguingly in the middle, larger than most but less complex than Pluto, with its own large moon and hints of activity. This diversity within a single dynamical class is profoundly telling. It suggests that an object's current properties are not solely determined by its present location or orbital dynamics, but were heavily influenced by its individual formation history, its original composition, and the specific collisions it endured before being captured into resonance. Orcus's unique characteristics, its bright ice, its dark material, its large moon Vanth, are therefore its personal history written over a foundation shared by all Plutinos. The precise orbital details of this resonant family offer another layer of insight. Not all 3:2 resonances are perfectly identical. There are subtle variations in orbital parameters like inclination and eccentricity. The fact that Orcus has one of the highest orbital inclinations of any large Plutino is a significant anomaly. This tilt could be a unique scar from a specific gravitational interaction, perhaps a close encounter with another large primordial object during the chaotic era of planetary migration that gave it an extra kick. Alternatively, its high inclination could be evidence of the gravitational influence of the hypothetical planet 9, whose proposed existence is often used to explain the peculiar, clustered orbits of the most distant extreme trans-Neptunian objects. Orcus's path might be a hybrid shaped first by Neptune's migration and later tweaked by another, more distant force. This interconnected web of resonant objects provides a natural laboratory for testing our theories of solar system evolution. By creating sophisticated computer simulations that attempt to recreate the migration of Neptune and the capture of the Plutinos, scientists can check their models against the real-world distribution of objects we see today. The specific orbital positions, inclinations, and sizes of bodies like Orcus act as a benchmark. If a simulation cannot produce an object with Orcus's exact parameters, the model must be refined. In this way, Orcus and its resonant kin are not passive subjects of study but active participants in a grand computational experiment, their frozen orbits serving as the answer key to a 4.5 billion-year-old puzzle about how our planetary system came to be. And so we arrive at our final, and perhaps most forward-looking, mystery, the future mission possibilities to Orcus. While our telescopes and computer models have revealed so much, the fundamental truths of this distant world remain locked away, accessible only by making the epic journey to see it for ourselves. The scientific community has taken note, and Orcus is increasingly spoken of not as a peripheral curiosity, but as a prime, high-priority target for a future dedicated spacecraft. It represents a unique opportunity to explore a world that is both a twin and an opposite to Pluto, a key that could unlock a deeper understanding of the entire Kuiper Belt's diversity and history. The blueprint for such a mission already exists in spirit, following the magnificent template set by NASA, a New Horizons flyby of Pluto. An Orcus orbiter, however, would be the ultimate goal, a spacecraft designed not for a fleeting glimpse but for a long-term residency. Imagine a probe slipping into orbit around this distant duo, its sophisticated instrument suite turning a blurry pixel into a dynamic, living world. A high-resolution camera would immediately resolve the debate over its surface, mapping the stark contrast between the bright, icy plains and the dark, mysterious regions in breathtaking detail, revealing cryovolcanic flows, tectonic fractures, and the true extent of its cratering history. But the eyes alone are not enough. To unravel the chemical enigmas, the spacecraft would carry a powerful visible and infrared spectrometer. This instrument wouldn't just identify the ices, it would create a mineralogical map, definitively identifying the composition of that perplexing dark material that has stubbornly resisted classification from Earth. Is it complex organic tholins? Is it primordial rock from the core? The answer would be revealed. A thermal emission spectrometer would precisely measure the temperature variations across the surface, pinpointing those anomalous warm spots and determining if they are merely sun-soaking dark patches or genuine windows to a warmer interior, finally providing concrete evidence for or against endogenous heat flow. The most thrilling data would likely come from a radio science experiment. By carefully tracking the subtle wobbles in the spacecraft's orbit caused by the gravitational tugs of Orcus and Vanth, scientists could map the dwarf planet's internal structure with incredible precision. This would solve the density discrepancy mystery once and for all, revealing the size of the rocky core and, most importantly, determining if a liquid water ocean truly does lie hidden beneath the ice. A magnetometer could provide further clues, searching for the faint induced magnetic field that would be a telltale signature of a salty, conductive subsurface ocean sloshing beneath the crust. The reasons for prioritizing Orcus are compelling and multifaceted. Unlike the more distant and scattered Eris or Haumea, Orcus's orbit is more accessible, requiring less energy and time to reach. Its status as a large Plutino in a stable resonance makes it an ideal archetype for its entire class. Understanding Orcus provides a benchmark for understanding the hundreds of other objects that share its orbital rhythm. Most importantly, it sits at a perfect sweet spot of complexity. It is not so simple as to be geologically dead, nor so complex and layered as Pluto that its signals are overwhelming. It is the Goldilocks world of the Kuiper Belt, just the right size to preserve fascinating activity while remaining interpretable, offering a clearer window into the processes that shape all mid-sized icy bodies. A mission to Orcus would do more than just satisfy our curiosity about a single world. It would write a crucial chapter in the textbook of planetary science, revealing the conditions that allow for oceans, geology, and perhaps even the ingredients for life in the most remote and frozen reaches of our solar system and beyond. As we bring our journey through these 25 mysteries to a close, it's worth stepping back to appreciate the incredible tapestry of questions that a single, distant world has presented to us. From its perfectly synchronized dance with Neptune to the possibility of a hidden subsurface ocean, from the stark color contrast with its moon Vanth to the unexplained spectral lines hinting at chemistry we don't yet understand, each puzzle is a vital thread in a much larger cosmic story. Orcus is far more than just a numbered object in the Kuiper Belt. It is a dynamic, complex world that consistently defies our expectations, challenging the very definitions of what an icy dwarf planet can be. The true value of exploring these enigmas lies not just in solving them for their own sake, but in how each discovery reshapes our broader understanding of the solar system. Orcus acts as a crucial benchmark, a control subject that helps us contextualize the wonders of Pluto and the strangeness of Haumea. Its orbital resonance is a fossilized record of Neptune's great migration. Its potential cryovolcanism teaches us about heat retention in small bodies, and the peculiar partnership with Vanth offers a masterclass in gravitational evolution. Every observation, every measurement, and every theory tested against this distant world refines our models of how planetary systems form and evolve, not just here but around other stars as well. It transforms the Kuiper Belt from a simple repository of ancient ice into a dynamic, diverse region with its own geology, weather, and hidden oceans. This exploration is a powerful reminder that scientific discovery is an ongoing conversation, a process of constant questioning and revision. The mysteries of Orcus are not dead ends, they are invitations to further investigation, each one a doorway to deeper wonder. They show us that even in the most remote and seemingly inert corners of our cosmic neighborhood, astonishing complexity and activity can thrive, pushing the boundaries of where we might someday find the conditions for life. The story of Orcus is still being written, with every new observation from Earth and every future mission proposal adding another sentence to its chapter. Now, we'd love to turn the question over to you. After delving into these 25 puzzles, which one captures your imagination the most? Does the gravitational ballet with Neptune intrigue you, or are you drawn to the possibility of a transient, breathing atmosphere? Perhaps the stark visual contrast with Vanth sparks your curiosity, or the idea of a hidden ocean locked beneath the ice fuels your sense of wonder. Share your thoughts in the comments below. Let's continue this exploration together, marveling at the fact that a world billions of miles away can still inspire such profound curiosity and connect us all through the shared joy of discovery.